Hello out there, welcome back once again. So our focus today, we'd like to do some revision, focusing on correlation and regression model. Okay, let's see what we have for you today. Okay, so I'll encourage you that while we're doing some revision, especially the focus is on problems. I'd like you to try some of the problems with us. Have a piece of paper, have a calculator with you. It's not really good just to observe without trying the problems. Okay, really encourage you to try at home. It's not about observing. To be successful in maths, it's about practice, practice, practice. And please try with us. Okay, fantastic. Let's see what we have. So, under correlation, okay, we'll look at, we know there's a line of best fit. Okay, the line of best fit and the least square regression, then correlation, linear regression, and interpolation and extrapolation. Okay, very important. I would like us to look at some of the terminology, the keywords. Correlation coefficient. What do we remember about correlation coefficient? What we know is that correlation coefficient is between -1 and 1. And correlation coefficient measure the correlation between two variables, the association between the two variables. Okay. For example, I might measure your maths marks versus your science marks. Does it mean if I have a good maths mark, I'll do well in science? Is there a correlation between the two? Okay. And what we need to remember about correlation also is that a correlation of 1 implies there's a perfect correlation. That's the strength of correlation. A 0 correlation, there is no association between the two variables we're studying. Okay, are we together? So correlation from weak, medium to a strong correlation. Okay, and we can do that using our calculator. Okay. And what about the least square regression? So the least square regression, we can do the least square regression using our calculator. It's actually the equation of what? Of the line of best fit, which is the least square regression, which is more a straight line, which is this form, y equals to a plus b x, which you can do using our calculator. Are we together? That's the least square regression. Then extrapolation. Now, we have our least square regression, or the best line of, the best line of fit. Now, when we want to predict or we forecast, if we predict outside the range of the data, we are extrapolating. And what does extrapolate really mean? If we're predicting outside the given range, the reliability of the prediction is not really that strong. Okay? That's when we extrapolate. We don't, it's too dangerous to predict outside the range, because we don't know the behavior of the pattern after the range. Okay. And what about the interpolation? The interpolation also is when we forecast, we predict using the least square line or the regression line. But interpolation is when we predict inside the range. And what is nice about the interpolation is that when we predict inside range, that's really good. We can rely on the prediction. We can trust that prediction without the range. The extrapolation, no. Okay, it's okay, but the reliability is the most important. Okay, because you can predict something and it might not happen. Okay, currently people have predicted the third wave using previous data. Is that really happening? Might be wrong because of the prediction. Okay. Are we all together? Because we're kind of actually extrapolating because we're using data And we're predicting that. Are we all together? We're extrapolating. Good. So, what we said, we're going to look at questions, okay? Application, because we know what is correlation, we know regression line, we know the line of best fit. And the line of best fit, remember, it must pass through the mean. Okay, good. Now let's look at our first question. Okay, and when you do your question, very important to read thoroughly and ensure that you're answering the right question. Sometimes we want to answer the questions, but we're answering the wrong questions because we're not reading the question. Okay, let's see. There's the question. So the manager of a hardware store records the number of staff that are in the store on a given day, as well as the sales generated per day. Are we together? So this is a store manager. So you have the staff, people working for a hardware, and how many sales and rents. How many sales they make. So here we had a day where there was 20 staff members, and what about the numbers of sales? Was 35,200. Are we together? And there was a day, only 5 staff members, but numbers of sales, 9,200. So that's the data. We read the question, we understand the question that it's a manager. What do you want? What do we have now is the staff members at work and numbers of sales. So our independent variable here is a staff member, numbers of sales. Let's see now. We understand the question. Now we go further. So the first question is, calculate the correlation coefficient for the above, then comment on the strength of the relationship. Are we together? So there we have the data. So what we have to do is to put the data in our calculator and calculate the correlation. Let's see how we do that. Okay. So there we have a calculator there. I already have my data. You can see my data there. So 20, I've put the data, 20 staff members, we have what? 35,200. And we have 5 staff members, 9,200. Okay, how we put our data? We put our data using the mode, then the table function. After that, we say AC. AC does what? Stores the data. Are we together? Then shift 1. Then we select regression 7. Then we want what? We want R. Okay, which is 3. Put 3 there. Equal. Then we get, let me round my correlation to 3 decimal places, then any instruction, very important. Okay. If R is, let's go back there. R is 0.9, let's see that, 0.975. That's the correlation. We calculate using our calculator. Okay, you put your calculator in state mode, you get a table, put all the data, AC to store what? To store the data, then shift stat 1. Are we together? Then you're able to select R for correlation. So we get a correlation of 0.975. What does it mean? This is a strong correlation because this is close to 1. This is strong correlation. Okay. There's a strong correlation. What does it mean? So it implies the more staff members at work, the more we have number of sales increase. There's a strong correlation between staff and sales and rent at the store. Are we together? Then as a manager, what does it mean? So it implies that if you have high staff members, will be profitable for this business? Are we all together? Okay, based on this correlation. Okay, fantastic. Are we all together? A strong correlation for that. Now, let's look at the next question. So the next question is, find the equation of the line of best fit in this form. So the equation of the line best fit is what? Is our regression model. Are we together? Let's see. We're going to use our calculator. We've already inputted our data in our calculator. There's no need to do it again. Okay? We just have to check the data. Let's look at that using my calculator. So if I say, okay, if I say AC, shift 1, are we together? I can select 2 to check my data again. If I 2, there's my data coming back again. Are we together? I don't have to put it again. My data is my calculator. So AC, okay, shift 1. Are we together? What am I trying to do? Let's look. We're trying to find the equation of best fit. Regression. I select 7. 7. 7, I need the A value. Are we together? I put 1 equal. What is my A value? So my A value, let's put my A value. A value is equal. Let's check again. A is 2788. 2788.26 if I round to 2 decimal place. 26. And what about the B value? The B value, still using my calculator. So the B value, I can go shift 1 again. Regression 7, and I want the B value, which is 2, then equal. There's my B value, which is 158. let's see again, 1658. So 1658.39 if we round to 2 decimal place. 39 if you round to decimal place. Are we together? So if you look at this, where's this regression? Let's look at our calculator again, because if we do that, so it's actually mode stats. So you're trying to find that. Can you see A, Y equals to A plus BX? Are we together? So we know that Y is A, BX. And we already have our A and B. What is our A? Is 2788.26 plus B is 165839X. So that's our regression. So we did find the equation of the regression. And I can use this to do what? To forecast, because X is staff, numbers of staff members. Okay. If I want to know the number of sales, if I have 6 staff members, I can use the regression model. Okay. Let's check our next question. Now, the manager, so we still have the same data, so the manager decides to use 19 staff members in his store. Okay. At the end of the day, this sale, okay, he used 90 staff members. At the end of the day, the sales is at 23,000. Will the manager consider this a successful day? Explain the answer. So the manager uses 19 staff members, and he gets 23,000. Is that good? So what we have to do is to use our regression model and use X as 19 and see what is the Y value. Are we all together? So we have our regression model in the previous page. Let's see, we can go back, use it from there. So we have our regression model there. Let's use that Okay, so I'm going to use my calculator. When I see X, I'll put what? 19. So let's use our calculator. Clear everything. So it's 2788.26 plus 165.8.39. What is my X value? Because the manager wants to use 19 stuff. So we get what? 34,000 something, above 34,000. But now, the manager used 19 and got what? 23,000. And what do we get? We get 34, 3. Okay, let's fix that. So we get 3, 4, what? 3, 4, 297, 297.67. 67. So we used our regression. Where we see X, we put 19. This is what we get. That's the expected. Using the regression model, the sales for using staff members should be 19. But the manager got 23,000. Was this a successful day? No, this was not a successful day. And especially because we are interpolating. Remember we spoke about interpolate. I'm predicting inside the range. So the prediction for this, I can rely on the above 34,000. That the expected for using staff members should be above 34,000. But the manager got 23,000. This was not a successful day. Okay, guys. Hope to see you after the break with more questions. And I hope to see you ready with your calculator and you're working on some of the problem with us. See you shortly. Hello out there, guys. Welcome back once again. So we looked at our first problem, okay? We calculated correlation. And what do we do? Making decisions using statistics, okay? So we're going to look at the second question and how we solve the problem. Let's see what we have, okay? So the second question, very important to read. So a survey was conducted at a local supermarket. So we have a survey. What is a survey, guys? You go out there in the street, you ask people questions, collecting data. That is a survey, okay? So it was converted as a local supermarket, relating the distance that shoppers lived from the store to the average number of times they shop at the store in a week, okay? Let's see what it does look like. So the results are shown in the table and the scatter plot. Can you see that? So if you look at this is the distance from the store in kilometers. And the average number of times per week they go to the shop. Okay? So if you look at there, so this is 1 kilometer and they go 12 times per week. That's the survey. So they went to one person, so how many times you go to the shop? Probably 12 times per week. And the person actually walks or uses a mode of transport or something, but this person's 1 kilometer. Okay, I think you can walk 1 kilometer. Okay? And the other person was 2 kilometers, and on average they go about 10 times to the supermarket, okay, per week. So we're given a table and a scatter plot was drawn for us. Are we together? Very important. Before answering the question, understand the question, break it down. We have a table and we have a scatter plot drawn for us. Where's the scatter plot? Let's see. Does it really correlate? So this is the distance from the store, kilometer, the average number of times shopped per week. So we can see here that 1 kilometer distance, there's the first person there we got, doesn't matter, and the 12, there's the point. So everything is drawn for us on a scatter plot. So here we give it a table and a scatter plot. Okay, let's see. Questions. Use the scatter plot to comment on the strength of the relationship between the distance a shopper lived from the store and the average numbers of times she or he shopped at the store per week. So what do we have to comment? The question is the strength of the relationship between, the strength of the relationship. By looking at this, can I look and comment on the strength of the relationship? Okay, I can. By looking at the scatter plot, I can tell what? The correlation coefficient. I can predict it or not, or just looking at this, if I have to draw the line of best fit. So the line, if I draw a line, let me see if I can draw. If I look at the points, they form a linear trend, a straight line. And if I have to draw that line, the points will be closer to the line. So this tells us there's a strong correlation. There's a strong relationship between that, okay? Between the distance from the store and how many times will a person go to the store. Are we together? There's a strong relationship. Yes, we can calculate the relationship and quantify that if we want to do, okay? But the first question is just comment. Did it say calculate? No. What if I calculate and comment? That's okay. But based on this, I can conclude by looking at the data that there's a strong relationship, okay, between that. Okay, good. Let's see now what we have. Use the scatter plot to comment on the strength of the relationship between the distance of the shopper from the store. So what we say, it says there is a strong relationship. There's a strong relationship. Okay? Or what do we mean? Strong correlation. Are we together? That's what we have. Okay? By looking at the trend, okay, because if I have to draw the line of best fit, all the points are clustered around the line of best fit. Okay? Great. Now, calculate the correlation coefficient of the data. You can see that the first question, there was no need for me to calculate the correlation coefficient. If I've calculated, yes, that's okay. Now, to calculate the correlation coefficient, I have to use my calculator. Let's see, using my calculator. So to calculate the correlation coefficient, I have to put the data first. Okay, let's clear the data. My table, so mode, stats, which is 2. Then I select 2 again, which is A plus BX, which is the regression there. Then I input my data. What do I have to put? It's 1 and the other side for Y because it's 12, okay, equal. Then I have 2 equal. Then how many times they go per week? 10. 2 goes with 10 equal. Then 3 goes with what? With equal. 3 goes with 7 equal. Then what do we have? 4 goes with 7 also. So 4 equal goes with 7. Then 5 goes with 6. 5 goes with 6. 5, 6. Then 6. And then we have 7 goes with 2. 7 goes with 2. Then 8 with 3. And the last one is 10 with 2. That's interesting. Can you see? The person who's actually, 10 kilometers away, they go to the shop on average twice. Kind of makes sense. I mean, you're 10 kilometers away. Do you really want to go to the shop 15 times? No. So hence, the first question was a strong relationship. Okay. Tens, you know, they went twice, okay? So 10 is twice. So now the correlation coefficient, we're going to say AC, shift 1, we select 7, regression, then R is the correlation, which is 3, equal. So what we see is a negative. We get R is R, 0.94. Okay, let's see again. 4, 6, let's take it to 3 decimal place. What does this tell us? There is so just calculate the correlation coefficient. It's negative. So it's a negative correlation. It's a strong negative correlation. Okay. So we could have seen, if we go back to the same question, we could see that if you look at our graph, can you see this has a negative gradient? The negative slope or gradient. So we can see there's a negative correlation, okay, association between that. What does that mean? If one increases, the other decreases. If I'm far away from where? From the supermarket, do I go a lot frequently? No, I don't want to go frequently. But if I'm near the supermarket, yes, you go and buy bread, you come back, tomorrow you can go and buy something else. But if I'm far away, there's a strong negative correlation between them. Okay. So there's a negative association. That should have actually been included there. Okay, now strong relationship, but this relationship is negative. So we have our correlation. We calculated it there. What is the next question? Calculate the equation of the least square regression line. So the equation of the least square regression line, we already have our data. What we have to do is just to calculate the A value and the B value. So we know that the least square line is y is A plus B x. So what we need to know is the A value and the B value, which will give us our least square line. Okay, let's see how we do that. So we have our calculator. So you can say shift A. We already have the data. 7 for regression. We need the A value. For the A value, we put 1 equal. That's what we get, 11.7. Okay, we get 11.7 for A value. Then what about the B value? The B value, again, shift 1, regression 7. I want the B value, which is 2, equal, which gives me a negative what? Negative 1 point what? If I round to 2 decimal place, 1, 2. 1, 2. So my equation will be y equal to 11.7 minus 1.12x, which is the equation of the regression. Are we together? We used our calculator to do the equation of the regression. Okay. Now, our next question. Given that the equation of the least square regression, so it's given by that, which calculated previously, 11.71 minus 1.2x. Estimate the average number that a shopper living 6 kilometers from the supermarket will visit the store per week. What does this mean? This implies if x is 6, what is the y value? So what we have to do is y is 11.71 minus 1.126. Then I'm going to use my calculator to do that, and let's see what we get. I'm going to clear that. 11.71 minus 1.12 bracket 6 equals to 4.99, which actually gives me 5, okay? So with 5. So what does that mean, okay? If I live about 6 kilometers away, on average, I'll visit the shop 5 times per week. Are we together? Makes sense, okay? Good. So now, the next one is, given that the equation of a least square line is this, which is the same we had, sketch the least square regression line on the scatter plot provided. So now how do we draw the least square line? What is important is that the least square line must pass through the mean, the average for x and the average for y. Are we together? But to draw that equation of a line is a straight line. I mean, I can find the x-intercept and the y-intercept and draw the line. Are we together? That's another way. Let's see that. So to draw that line, I know that my y-intercept is about 11.71. So it should be around somewhere there. Are we together? And x, can I find x? I mean, I can find x because I have the equation of the least square line by making y 0. Okay? If I make y 0, if I solve for x, I move 11 point. Let me move the x the other side. I get 1.12x is 11.71. So to do this, I divide both sides by 1.12. Let me get my calculator. So let's divide 11.71 divided by 1.12. So that gives us our x value, so which is about 10.46. 10.46. So 10.46. Oh, somewhere there. Okay. But what is important also, we have to calculate the mean. Okay. Another way to calculate the mean. What is the average for the distance and the average for numbers of shops? So just you have to indicate that this passes through the mean of x and the mean for y. Let's see, we still have our data because we have the data. We can check the mean. Let's see, shift stats. So let's look at our data. We still have our data, agreed? Which is there, okay? So shift stats, let's look at that. Let's look at 5. So the mean for x, I can select the mean for x. Are we together? That x bar, I put 2, which is 5. So x bar is 5, which is the mean for x for the distance. Now, what about the mean for y? What does it mean? The average number of times someone goes to the shop per week. Let's go back and do that. What is the mean for y? Okay, shift 1. We set for 5. We select 5 there. The mean for y, we select 5 again. We get 6.13. 6, okay, let's go back. 6.13. So it's very important that your least square line passes through the mean. So the mean, actually, it's the x value is 5, which is there. The mean for y is 6.12, somewhere there. Are we together? 6 somewhere there. So actually the least square line should pass through the mean, can go through that point, but pass through the mean all the way. This is what we get. So it must pass through the mean. that's the new point you create, which is 5 and 6.13. Very important. That's how we draw the equation of the least square line, okay? Because we can see the y, which is easy. I'll say find the mean, and it passes through the mean. Okay, guys, I hope it makes sense. We'll see shortly after the break with another question using correlation and regression. See you shortly. Hello out there. Welcome back again. We are still on revising. We're looking at correlation and regression, okay, to answer some of the questions. Okay, so let's see what we have in our next question. So our next question here, very important to read. Read, read, read. It's pointless to answer the question because you might be answering something wrong, okay? The times achieved. Those are the times achieved by winners of men's 100-meter swimming events at the Olympics game from 1972 to 2004 can be accessed from this website, okay? So the scatter plot was shown, okay? So here we have data from 1972 to 2004, but this was men's Olympics, swimming, the times they finish. Okay. For what? What event? Are we given an event? A 100-meter event. Are we together? Let's see what we have now. So the 100-meter event. So there's a scatter plot. Those are the times for men. So there's a scatter plot. You can see that in 1972, so the times, I mean, this is around 50. We can see there, I think it's around 50-something seconds, you can see, in 1972. 1976, it's 50. You can see 1972, we're getting 50 seconds. So I read my questions. We have men's Olympics from 1972 to 2004, 100-meter event. Times. Okay. What do we have to answer now? Or read some more. Let's see. Okay. Indicate whether a linear or quadratic or exponential function best fits the data. So the scatter plot of times taken by winners for men for 100-meter at Olympics. Okay. So looking at this, is this linear, quadratic, or exponential? What will you go with? Linear. Why linear? Quadratic or exponential? I will go with a linear relationship. I think this is a linear relationship because the data given here follow a linear trend. Okay, I can draw kind of a straight line. If I draw a straight line, the points will kind of be not deviate from the straight line. Not a parabolic, okay? Maybe some might argue and say exponential. Why not exponential? I'll go with a linear because a linear will capture most of the points on our data set. So there's a linear relationship here. Linear, okay, that's what we'll go with. We together. Okay, good. Let's look at the next question. Now, draw a line of best fit for the data on the graph. So now we have to draw the line of best fit. So just to remind you again that the line of best fit, okay, I kind of drew it. If you look at that, I said, okay, if I draw that this is my line of best fit. But I didn't say this is a line of best fit. I was him explaining where the data follow a linear trend. But when you draw the line of best fit, it's very important to calculate the average for this and the average for that. Because the line of best fit must pass through the mean for that. Are we together? Okay. Let's see that question. So we're talking about the line of best fit. We have to calculate the average times, but the times are there. Can you see? It's not exactly 52 51s. Those are the times. Those are the average times for all those points. Can you see that? If I do that, this is what I get. Okay, this is my line of best fit. My average, somewhere there. So the mean for X and the mean for Y. Very important to indicate that point. Okay? You can calculate that point using your calculator. So the average is the mean for X and the mean for Y, and the line of best fit is that. Are we together? Okay, that's my line of best fit. Okay. So let's see now the next question. So here, describe the trends that is observed in these times. Give one reason for this trend, okay? So what is a trend? We can see, what does a trend mean here? We can see that every year, on average, we can see that men's swimming team, they're just getting better and better. They're reducing their time if we compare from 1972, which is actually the highest. And if you look at 2000 to 2004 there, actually they're taking less time to finish the 100 meter. What could be the reason? Okay? Could have been getting better with time, or also using more technology or training better as swimmers, because they're getting better every year. But also we can see there's kind of an outlier there, something different in 1988. Okay? They could be getting better because of training better. Are we together? As swimmers, this is what is happening. It might be one of the reasons. Okay? Because they're definitely getting better. That's the first. Now, let's see what can be said about the effort of winners in 1976 and 1988. Sure. In 1976 and 1988, what can we say about those two? If you look at those points, so there's a huge deviation from the line of best fit. Are we together? So those two are outliers. Okay? Are we all together? Outliers. So, I mean, according to our regression model, they should be, in 1988, they should be performing there. And 1976, they should be performing there. They're not performing at the best in those 2 years, in 1976 and 1988. Okay? Could have done better according to our regression line. They are far away from everyone. Are we together? Great, fantastic. Okay, now let's see what we can do here. So, use the line of best fit to predict the winning time in 2008. What is the winning time in 2008? 2008 is somewhere there. So the winning time will be, we have to go on our line and predict. But also looking at 2008, okay, we're kind of extrapolating also. Do you believe that? Is that accurate? Remember, when we interpolate, if we predict within the data, which is somewhere there, the reliability of the answer is really good, but outside, the reliability is not that really strong. Okay, let's see what is happening in 2008. Actually, in 2008, okay, this is what we get. 47. Okay, that's what we get. It's 47 seconds and 0.21 seconds. Okay, are we together? And this is the person actually won. It's Alain Liban, France, in 2008. You can check that. You can, if you have time, try Google that and see that's the actual time in 2008 for the winning person. Okay, fantastic. So now let's look at our summary. We looked at correlation, we looked at the line of best fit, and we looked at linear regression, interpolation, and extrapolation. Okay, very important. Correlation, we're talking about association. Strong correlation, no correlation, or weak or negative correlation, or something of that nature. It talks about association between the two variables. The line of best fit is what? It's a line, a straight line, okay, on a scatter plot, but must pass through the mean. That's the line of best fit. And the linear regression is the equation of the line of best fit, which is given by this line, y equals to a, bx. We can do that using our calculator. When does interpolation and extrapolation comes in? When we want to predict. If we predict inside the range, we're interpolating. And the reliability of our forecast to predict, very strong. We can rely on that. But extrapolations outside the data. And, the prediction might not be that accurate. Okay? Fantastic, guys. We have come to our end of our lesson. I hope you enjoyed. And we really encourage you to work continuously. And it's okay to struggle with mathematics. It's normal. But to get through that, to fight those challenges, is to work consistency. Consistency is the key. And emphasize again, we don't work just because we have an assessment or test coming. We work even when we're okay. We work even if we understand, do some problem to previous paper, okay? And seek challenges when there's time, not because you're writing a test next week or tomorrow. We hope to see you soon and keep the good work going. Cheers.